Yeah, okay, go on.
Very nice. So yeah, everyone, we're being recorded. Today we have the 14th, I think, seminar in our Tunneling in QFT series. We have Maciek Kiekler from the University of Warsaw. Just like to highlight, we have the next few lined up. In April, we have Thomas Steingasser, then in May, Matthew Johnson, and then in June, we have Anna Kormu. Yeah, but today we have Maciek talking about finite temperature bubble nucleation with scale shifting hierarchies. Yeah, please take it away.
Okay, so hello everyone. First of all, thanks for having me here in this wonderful series of seminar. And yeah, so I'm a PhD student at the University of Warsaw. My supervisor is Bogumiła Świeżewska, and today I'm going to talk about very recent work actually, about well, improved calculation of nucleation rate in the context of supercooled phase transition, but also the implication for, I would say, more general class of models. And yeah, this project appeared on arXiv. Yes, oh, sorry, spoilers. Yesterday. Here's the number, and this was done in collaboration with Filip Szycho, Thomas Tenkan, and Jorinde van de Vis. So to begin with, some general intro. We know, I'm assuming that most people in the audience know what is a cosmological phase transition, but basically we are interested in a scenario where kind of in this QFT setup, we have the scalar field, which have a temperature dependent potential, and at large temperature, this potential is kind of parabolic shape. So we are stuck in this so-called false vacuum here. And then as the temperature drops down, then the second minimum appears, and at some point, the field can transition into this global minimum or true vacuum. And in the point of view of kind of cosmology, this process looks as a nucleation of bubbles filled with this new phase here, while the rest of the universe is in the old phase, and those bubbles appear, expand until they fill all of the space. And we are all excited because there's a lot of physics connected with those bubbles. And also we know that they can produce gravitational waves, which we'll be hopefully able to observe in detectors such as LISA. And those bubbles, the creation of these bubbles is predicted by BSM theories, basically. So it will be also a smoking gun for some new physics besides standard model. And usually I think, like in my view, that connects those two pictures is the bubble nucleation rate, which tells you basically how many bubbles are nucleated per Hubble volume, and you calculate it from this field theory setup you have. And in this talk, I'm going to be focusing exactly on this guy here and show some theoretical uncertainties associated with going from this step here, and what are then the implication for the bubbles. So the outline is as follows. First, I'm going to do a quick intro to nucleation rate. I hope there are a lot of experts in the audience, so I hope it won't be too trivial. And then I'm going to introduce our playground, the model for featuring a supercooled phase transition. I will discuss how the nucleation rate looks within this particular model, and there I will talk about some theoretical uncertainties and basically different recipes how to compute this nucleation rate. And then I will show the results with what we believe is right now the most accurate approach we've cooked from those recipes. And yeah, and maybe some outlook. Okay, so yeah, first bubble. So the overall formula for the thermal bubble nucleation rate, so this transition caused by the thermal fluctuation, can be separated into two parts. So first we have the dynamical part, which encapsulates those non-equilibrium effects, and this has dimensionality 1 of t, right? And in the so-called no damping approximation, it can be computed by this formula, where this is a negative eigenvalue of the nucleating scalar. Here are some references if you're interested more about this case. And then you have also the more dominant statistical part, which captures equilibrium effects. And in this talk, I'm going to focus completely on this part only. And this part can be computed basically by computing the effective action within your theory on some specific background, which is going to be the bubble. And this background is a solution to Euclidean equation of motion. And this has dimension t to the 3. So the whole rate has dimension t to the 4. And what we want to do is to compute then this. So we want to compute the statistical part, and we want to compute then this effective action on some background. But of course, like, doing this completely is, I don't know if even possible task. So we want to do it in some perturbative expansion. So we can expand it order by order on the background, and then it turns out that we can go to NLO just by using the leading order background. And some spoilers, like this leading order action is mostly coming from the one loop effects, and the next leading order also contains some two loop effects. So, but here I'm going to now focus on the one loop stuff. So how to compute this effective action? Well, let's consider some toy model where we have a global U1 symmetry. So then we know that this statistical part of the nucleation rate is given as the effective action evaluated in this background. So in order to obtain this effective action, I want to calculate it using the so-called background field method. So I have this path integral that I need to perform. So I have my kind of 3-level classical theory that contains this scalar field, Goldstones, and some chi, which is here kind of as an actor that stands here for any other field in your theory that you have. And then you want to expand this H over the background, right? And then if you just interested in the one loop level, you can perform this integral because this is basically, those are only like Gaussian type of fluctuation. And what you obtain is this product of determinants, so-called fluctuation determinants, and this exponent of the original action that you had, right? But now it's only depending on the background. All right. So you get from the scalar fluctuations, you have the scalar determinant that also contain this familiar factor that you usually see when you see the formula for the nucleation rate. You have the determinant for Goldstone and also for this chi fields, which in our case is going to be a proto vector determinant. And this guy is dimensionless. It's actually can be put into inside the exponent, and it's actually like a one loop correction to this 3-level action. All right, so we want to do exactly the same thing, but now in a specific model, and this that features supercooled phase transition. So, okay, what a motivation? Why supercooled phase transition? Well, recently they're kind of popular, I think, because of the PBH production prospects. Like you have those very slow papers that show that if you have very supercooled phase transition, which means usually slow transitions, you can produce primordial black holes. So, and explain dark matter with them. Also, you can have so-called secondary gravitational waves. And another thing is that people have been trying to fit signal from gravitational waves from supercooled phase transition into PTA data. It's not so robust, but another feature is that those kind of transition, if you think about the potential gravitational wave signals we can observe, give you a benchmark for studying the strongest possible signal, like this limit of the strongest signal. And we know that LISA is coming, and I hope other experiments. So we need to prepare some robust framework. So that was the goal of us. So the model we are considering here that has all of those features is called SU2CSM, and it's basically just the standard model without the Higgs mass term, so it's classically scaling variant. And then we have also an additional SU2 dark sector, and in this dark sector we have a new scalar field, which is a doublet of this SU2, but singlet of the standard model. So we have two scalars, Higgs and the new scalar, and in the 3-level potential, you see that the interaction between those two sectors is only by the Higgs portal term. And then, of course, we have a new gauge boson associated with this SU2. And later I will going to show you some results for the parameters for the scan of the parameter space of this model, and you can measure using the measured Higgs wave and mass. We can choose three parameters of the model such that there are only two, which is this dark coupling and this mass of this new gauge boson. So those are going to be the thing that you see on axis later. All right, so why we have this classical scale invariant potential? Well, because model. Well, because those kinds of model give you this supercooling for free, and this can be kind of hand wavy, easily understood by the fact that those models feature a flat potential near the origin of the field space. So when then the barrier that's necessary for the tunneling for the bubbles is generated by the thermal corrections, and even the slightest correction is going to give you this bump here. So turning around this argument, the barrier lasts till the very t equals 0. So that's why you can really be trapped in this false vacuum here and supercool to low temperatures. For example, if we talk about electroweak-ish phase transition, we can go from up to even QCD scale with the percolation temperature, which is completion temperature where the transition is completed. And of course, because you supercooled a lot, there's a lot of energy stored, like the difference between the minima is large. So you always have a strong gravitational wave signal. All right, so having this setup, and we are now mostly interested in this dark SU2 scenario because, sector, because the phase transition actually proceeds there. So first we have the tunneling in this by this new dark scalar in this direction, and then the field in the potential, right? The field rolls down to the minimum where both Higgs and mu scalar have non-zero wave, but the tunneling itself is only in this SU2 sector. So we basically are interested in a setup SU2 plus scalar. So that's quite simple actually to study. And of course, the most robust way to include thermal high temperature effects that actually drive the tunneling is to use methods of EFT, so-called dimensional reduction. So if we consider a thermal field theory in the imaginary time formalism, and we are interested in equilibrium physics, so we can do that, then the fields right, can be decomposed into the so-called Matsubara modes. So they live right now on this 3+1 dimensional manifold, where the time dimension right now is this imaginary time is proportional to 1/t, and it's warped. And those fields can be thought of as a tower of states made of those Matsubara mode, given by this omega here. And then, since we have this hierarchy of scales, that those higher modes are much heavier than the zero mode, which is actually important for the tunneling, we can integrate out those UV modes, so all of them that are non-zero, and then what we end up with is actually a simpler theory in 3 dimensions, right? Because I got rid of this power which was making my temporal dimension. So I'm right now living in the 3D world, 3D EFT, where before I had the scalar, the gauge boson, and the 2 couplings, and the scalar was massless. But then after I'm constructing this EFT, I'm ending up with a scalar living in 3D, the spatial gauge modes, and the temporal gauge modes that right now are kind of acting like a separate scalar field. And the scalar field gained a mass due to some temperature effect, and also the couplings have a temperature corrections. But the important thing here, I think, is that when you look at this 3D theory at the first glance, you don't really see the temperature anywhere. You just have a simple polynomial potential, and all of the temperature dependence is really encoded into those parameter couplings in this 3D EFT. So this is what we given some more specific look at this. This is what we end up with. So as I said, we have the scalar and gauge modes living in 3D. So, but the temporal mode is right now living separately. And as I said, the M3 is the mass of the scalar mode gets a temperature dependent mass. Then this MX3 is just the 3D mass of the gauge spatial modes, and it looks pretty normal. And then we also have a temporal modes that also gain this thermal mass. And this S3 is corresponds to this S3 that I showed you before, this three-level action upon which we are going to we want to calculate effective action in order on the bounce background in order to get the nucleation rate. All right, so we can do that. We can calculate the effective action using the background field method, and what we end up with is this product of determinants. I'm kind of abusing notation here, so I'm just, it's kind of like a sketch. So first you get the scalar determinant, and you have the separate determinant for those temporal modes, but then you also have a third determinant, which is vector Goldstone determinants, because those modes are mixing on this non-trivial background, and this is the most difficult thing to compute, I would say. And and then you also have this dynamical prefactor, as I mentioned at the beginning, and I included it here because those simple determinants actually can be easily computed using this nice package called bubble-nucleation. You just really take the Cosmo transitions, for example, Cosmo transition output for the bubble profile. You put this into this package, and it spits out the values of the determinants, and this is nice. So those two guys actually give you this prefactor to the exponential to the rate, and then in the exponent you can include those two guys because they are dimensionless. And as I said before, that then we can think of those as the one loop correction to the effective action coming from the gauge, this mixed gauge Goldstone determinant and the temporal gauge modes. All right. So then, of course, usually when you are an average gravitational wave plotter, you don't really want to compute those determinants because, as I mentioned, those are easily computed right now. You can have this, use this package, and it's nice. But this guy is quite complicated. Yeah, I would say, because I had to compute it eventually. Spoilers. And usually what you can do instead, you can use the so-called derivative expansion. And yeah, so let's start with this simplified approach first. And this is what we've done in our previous paper, by the way. So we have this determinant, and we can expand it in the so-called derivative expansion. And this expansion relies on the fact that the mass of those gauge modes must be much smaller than the nucleating scalar mass, right? And then when you expand it, you kind of arrive at the very familiar term, this cubic term, which is actually the barrier generating term. So if you go back a bit here, right, so at this kind of three-level action, we didn't have the barrier in the potential. So it's really generated by the gauge modes. And then if you, in the next to leading order, what you obtain from this determinant is the so-called Z factor, and this leading order and NLO corresponds to the LO in the expansion of the effective action, right? So there are two expansions. One is the derivative expansion of this whole thing, which is just the one loop fluctuation determinant for gauge modes, and then you also have the expansion for the whole effective action, and you know, the part of this determinant goes into the leading order, and the other part goes to the next to leading order in the expansion for the effective action. And of course, you can have higher powers in derivatives, and they will be also included, I think, at NNLO in the expansion for the effective action. So if you use this derivative expansion, what you end up with is, as I said, at leading order, you right now have this modified potential that contains cubic terms. I'm also included here the temporal modes. And then at NLO, you have this Z factor that was also coming from the determinant. And also you have this VNLO, which is a two-loop gauge effect. Okay. And then if you have that, you can calculate the effective action and then nucleation rate perturbatively. So the first recipe, the NLO grad recipe, is that you obtain leading order bound solution using this action. Then you evaluate both leading order action and next to leading order action, this one, on this leading order solution. And having this action, you can calculate nucleation rate just like this, just by putting this in the exponent. And in this recipe, we use for the scalar determinant, and for the dynamical part of the prefactor, we just use dimensional guess for this prefactor. And this is simple. However, there is a problem, obvious one, an elephant in the room. And this is the problem of the so-called scale shifters. And I think it was, it was called for like this for the first time in this paper, I think. So the main assumption that allowed us to expand this determinant and not to compute it directly was the fact that these gauge modes must be heavier than the nucleating field. However, since the gauge modes have field-dependent mass, if you evaluate on the bounce solution, which interpolates between the false vacuum and some escape point, right? You can see here. So on this plot, on the x-axis you have the bubble radius, right, and y-axis is the mass, some mass scales, and here you have the scalar field mass, this M3. And then you have field-dependent mass of the gauge modes. And for the temporal one, it's nice because it's protected by this MDX term, and it's always heavier than the nucleating scalar. So the derivative expansion always works, so you can use it safely, but you can also use bubble because it's better. But for the spatial gauge mode, inevitably at some point, the so-called RT, you get into the trouble. So yeah, this T stands for the tail of the bounce, or for the trouble, because then your gauge mode becomes lighter than the nucleating scalar, and your derivative expansion breaks down basically. And in the previous work, we used this approach, and we obtained a finite contribution from the derivative expansion from this z factor over here. But we know that there is some error introduced, and if you look at this integrand here, right, that gives you the next to leading order correction to the whole effective action evaluated on this bounce background, you see that actually this contribution from the kinetic factor, so the first non-zero momentum term in this derivative expansion, is dominating over this V and LO, and our trouble starts here. So basically, we get a finite contribution to the effective action, but we don't. Back then we didn't know how much. We know that there is an error, but we didn't know how big the error is. And then you might ask, okay, but this contribution is finite, and so what happens at higher order terms in derivative expansion? So instead of just truncating this here, I'm actually computing those other terms, and what I'm getting is these operators proportional to the higher powers in derivative. And what turns out that if you evaluate them on the bounce solution, all of them are actually just divergent at large radius. So it's not even a finite contribution at this point. And even this Z factor that I showed you before, if you compute it at 2 loops, it's also divergent. So we are sad because I think it's time. There is no escape. One needs to actually try to see and calculate those fluctuation determinants directly. So that's some memories of mine from last year. And yeah, so let me get to the next part, how to compute those fluctuation determinants and how big the error is, basically. Okay, so again, going back to some toy model where I have some nucleating scalar and this some field chi, and there is some coupling kappa between them. I'm obtaining in this when I do the path integral over the Gaussian fluctuations, I'm obtaining this determinant that stands in front of the exponent. And what I want to do now is to first use the spherical symmetry of the bounce solution and I can decompose this determinant into spherical harmonics, and I'm getting this product of those determinants. And then I can use Gelfand-Jagland theorem, which basically reduces this problem of computing the determinant of this operator, so set of product of eigenvalues, to just solving two differential equations and taking their infinity limits. So I'm not going to go into the details here, but there is just this nice method that can be used. And there are some problems that you have those zero modes that need to be removed. This product can be carried only like numerically to only some finite L, right, in this spherical harmonics product. And then, of course, this product is generically UV divergent. However, all of those, for a case of simple operators like this one, for example, where we have just one-dimensional thing here, they are handled by bubble-nucleation, so this is nice. But then there is this gauge Goldstone determinant, which looks very ugly because instead of just 1D thing here, we have a whole matrix of those modes mixing. And then there is no bubble-nucleation tool that would calculate it instead of me. So we had to include it ourselves, and we did it, basically relying on this implementation described in this nice paper here, where Andreas was studying the regular SU2 plus Higgs, but since this model is very similar, we were able to use those results and implement them in Python and solve them numerically. And then finally get a very PhD student to do all of the scans for parameter space. So if you can compute this determinant, how are you able to then calculate the whole nucleation rate? So this is NLO det recipe, and this is so far the best thing I think that we have right now. And this actually idea was also mentioned in this, I mean not mentioned, but given in this paper by Oliver and Jonas. So what you do is, again, first you start with using the leading order derivative expansion, because you need this barrier generated, right? And actually, we checked that at leading order, this term, this derivative expansion works pretty well, very well. So you can obtain the leading order bounds, and then, but then instead of evaluating all of the terms on in derivative expansion on this bounds background, you instead evaluate the determinants of the background, right? So you did this swap. Okay, so we did it for basically for all of the determinants, and then for the next to leading order contribution, this two-loop thing, we actually use the derivative expansion, because then stuff gets really ugly. You don't really, I think at two-loop you don't even have those determinants. You need to use some numerically evaluated green functions, and yeah, Thomas sent me once some old Russian paper about it, but I think it's definitely for the future work. But anyway, in our new paper, we also show that this contribution for the effective potential two-loop also behaves well, because as when you are going into this tail of the bounds where you introduce the error, actually the contribution for the next to leading order effective potential is also very small. So you get an error, but also thing goes to zero. So you don't really get. I would say that this is anyway pretty accurate. And then if you have all of those ingredients, you can calculate the effective action. So you evaluate the leading order action, but you need to subtract this part coming from gauge Goldstone determinant, because it's already there in this determinant, right? So if you add this thing, you would be double counting. So you need to remember about that. And then you also get this NLO to loop thing from gauge bosons, and then finally you can also get the prefactor in form of scalar and this dynamical prefactor from bubble-nucleation, and this is the best thing that we were able right now to cook. So let me show you now the results. Oh, I'm pretty good on time. So this is a direct comparison of the effective action for one benchmark point in our model. So this benchmark point corresponds to mx 10 to the 4 GeV and gx, the dark coupling 0.8. And so right on the y-axis here, you have the effective action evaluated on this leading order bounce solution. I mean, it's the whole nucleation rate, so it also contains this dynamical, but we expressed it in such a form that everything is sitting in this exponential. Okay, and then on the x-axis you have the temperature. So at large temperature, this thing is large, so the nucleation is not there, and at some point you cross this line, which is given by the requirement that gamma over h to the 4 is equal 1, so you have at least one bubble per Hubble volume nucleated. And those line corresponds to different approaches. So first you have the blue line is just the leading order in our expansion for the action in the 3D EFT. Then you have the daisy resummation approach in this lighter blue, also called agnostic approach in some papers. Then this orange line is the line that we obtained in the previous work using only the gradient expansion, so having this scale shifter problem. And then the green line is the best thing that we have right now, this NLO det recipe. Okay, and all of those curves, except for the solid green, this NLO det, have this exponent prefactor in the nucleation rate approximated just as the t to the power of 4. And also this in this dashed line, we computed green dashed line, we computed the determinants of gauge modes. But for this prefactor, we also just set this simple approximation just to see how big difference it gives. Okay. So the main result is that indeed the error coming from breakdown of gradient expansion or from those scale shifters is noticeable. And you see that if you just naively compute the effective action using derivative expansion, you overestimate it. So you have the nucleation earlier, right? Higher temperatures. However, still the biggest difference comes from the actually adding the next to leading order effect to the leading order action. And another thing is that is kind of separate, but here we can also, so those bands correspond to the varying the RG scale in this 4D theory, so this parent theory, for which we then construct 3D theory in order to get the nucleation rate. And you see that as expected for the most, I would say, basic approach, daisy resummation, this band is the largest, and then it gets nicely reduced. So actually not only this approach using the 3D EFT not only reduces your RG scale dependence, but also it turns out to be gauge independent. So this is actually the approach that allows you to provide robust predictions for your model. Okay. And then we've performed scans of parameter space for this particular model for two phase transition observables. So first, here you can see the percolation temperature. So as I mentioned before, on the axis you have the free parameter of the model. So on the y-axis you have the gauge coupling, and then on the x-axis you have the mass of this dark gauge boson. So this plot here was done for this point over here. And on the left-hand side, you see the predictions, our best predictions right now for the percolation temperature. So the temperature when the transition, where the bubbles percolate and the transition completes. And yeah, we have excluded sector. So first excluded sector is here where we are not able to reproduce the correct electroweak minimum for the Higgs. Then in this corner, just when you run this coupling here, which is defined at the true vacuum state of the theory up to the smaller scale relevant for the tunneling, it just blows up. So we can't really do anything here numerically. And here, it's not really excluded region, but this is the moment where we supercool so much that the percolation temperature just becomes of order TQCD, and then we would have additional effect than just regular electroweak phase transition, right? That here we would also have this effect from the quark condensation. And this region here corresponds to a moment where you supercool so much that you have a lot of energy trapped in the universe, and you always enter into this period of thermal inflation. And here in this region, you actually the bubbles are not able to percolate successfully, and you don't know basically when exactly your phase transition is happening. So we just excluded this region because we weren't able to figure out exactly when stuff is happening. Okay, so you see that, as I said, that indeed in this model you can supercool a lot, and you can get the percolation temperature range from TQCD up to 200 GeV. And then, so this is the best approach that we have right now. And then the question is, okay, so how big was the error coming from those scale shifters and using the derivative expansion at next to leading order? So comparison between those two recipes that I showed you. And it turns out that it's quite large. It's up from the 40% up to even like 300% in this, when you go to this non-percolation region where the transition is most supercooled. So usually this is the stuff where most stuff breaks. This is the region where most stuff breaks down. Okay. And then similarly, we can I can show you the predictions for the average bubble radius. So this is another important parameter. So parameter also for the gravitational waves, because this is not also this is giving you well, it's important for evaluating the peak frequency of the signal, but also for the amplitude. And this R star H star basically tells you how much of the Hubble radius is like this is the average bubble radius in the rescale to Hubble. So we can have the smallest bubbles are of order 10% and the largest one of even of the half of the horizon. But then you of course get to the no percolation problems. And then the error from the scale shifters for those predictions is smaller, but still it can be up to 22% when you go to this region of the largest supercooling. And this is consistent with the previous result that we found where we were comparing the relative difference of just the daisy resummation results and the NLO, but gradient expansion approach. And we also see that percolation temperature was more sensitive than bubble radius, and this is not such a large difference, but it still can be important, and especially for those predictions for the primordial black holes production in those very supercooled phase transition. Because here, as you can see on this plot that I borrowed from some colleagues, on the y-axis you have the inverse time duration of the phase transition, which can be translated easily to the average bubble radius at the end of the transition, right? Time passes, bubble grows. And you can see that if I move on this axis a bit, I can get from no primordial black holes to all of the dark matter explained by the primordial black holes, or dark matter or primordial black holes overproduction. And so even this 20% discrepancy, error can lead to some serious change of predictions. And I would say this is kind of ongoing topic, because recently there were new results by Jan Noir and his colleagues that maybe primordial black holes are not so easily produced in slow supercooled phase transition after all. So we'll see how those PBH wars are going to end. And then finally, I would like to just show the direct influence of this gradient expansion breakdown on the percolation temperature predictions. Because before I have showed you the comparison between our previous approach using the gradient expansion at NLO and the best approach that we have right now. But this best approach that we have right now also computes those scalar determinants and dynamical prefactor exactly using the bubble that. But if you want to just see the effect of gauge mode determinants, you need to have the same prefactor there, right? So this t to the 4 that we used here. So right now I will be showing you the difference between this result for this solid line here and the dashed line here. Okay, and sorry. So here on the right hand side, you can see that still the error solely from the scale shifter is dominating, and it can still be quite very large. So before we had above 300, right? 300%, and now we have 2.7, but it's still very large. And then so this is important, I would say, important to actually, in the end, take care of those determinants properly and not rely on the derivative expansion at NLO at least. And then, okay, as a side note, on the left-hand side, we have the relative difference for the predictions where you compute the gauge determinants exactly, but then you change this prefactor, you either computed the scalar determinant and the dynamical prefactor using the bubble depth, or just set it to t to the 4. And here the difference can be also quite large, up to 36% again in this most for the most supercooled scenario. But this error is not dominated. It's dominating. It's still there, but the biggest error comes from the breakdown of the derivative expansion and those scale shifters. Okay, so then going back to this issue of the prefactor, there is one thing that we found, and it's quite peculiar, I would say, is that what we found is that if you compute the prefactor exactly, so using the bubble that, including this adynamical, and then approximating this prefactor just by T4 instead of T4 times this S3 over 2 pi that you sometimes see in the literature, it turns out that actually this simpler approximation gives you a better agreement with the actual result from the exact evaluation of the determinants. So here on this plot, you can see the predictions for percolation temperature as a function of Gx for a constant mass. So we are moving in basically this line here. And on this plot, I was showing you the relative difference between the exact scalar determinant and t to the 4. So this is the solid line versus the dashed line. And then you can also add this Jacobian that's usually there because this is something that you can also easily compute instead of computing the whole determinant. And it turns out that it actually overestimates the percolation temperature, and just you get better agreement when you just use t to the 4. And this is what happens in this model. Okay, so that's it basically. Yeah. So let me sum up and give you some take-home bubbles. So first of all, if you want to have reliable predictions for supercooled phase transitions, you need to include those NLO corrections because they are actually quite large. Then it turns out that derivative expansion introduces significant errors, so you can't really trust it. And moreover, it's going to break down if you are going to move above the NLO. And then including the full scalar determinants is also important, but it's not such a big, it's not bigger source of error than derivative expansion breakdown. And the clear result is that we found that this T4 just works better than T4 times this Jacobian. And then I would say, so this was done for a supercooled phase transition, and these conformal models and are not, you can't really put them on the lattice to, well, it would be nice to see whether we are actually converging to a with the result for nucleation rate. And in case it was conformal models, you can't really do it, I think. So it would be nice to also just perform this whole well, beautiful computation for a more regular model and see how accurate we can get. Yeah, so thanks for listening, and yeah, please ask question.
Thanks a lot, Maciek. Yeah, please, people in the audience, raise your hands or to ask a question. Or if you can't manage that, just unmute yourself. But thanks a lot, Maciek. Very impressive work computing this mixed determinant.
It was following Andreas, but yeah, cunning
but
was the
following
worst.
Andreas is not always so easy. Yeah, any questions from the audience? Okay, we have Elia. Please go ahead.
Hi, that was a great roller coaster. Very interesting. I just had I still don't know if this is a silly question or not, but like how much of this would survive if we let go of the assumption of the spherically symmetric solutions to the bounds at finite temperature?
I mean, so first of all, I don't know how one would compute those determinants then. So because you rely on this decomposition to spherical harmonics, and you can use this Gelfand-Diagonal theorem. So maybe there is a way, but to be honest, I don't know. And then
maybe in other words, like let's say it's almost spherically symmetric. Do you expect that deviation from that spherically symmetric kind of solution would have a huge impact? Or it's a hard question, you know, but like, what's your intuition, your feeling?
Well, so in principle, so all of this kind of derivation, maybe I will go to the beginning and have an excuse to think of an answer. But yeah, here, so when we evaluate this effective action on this solution, you use this saddle point approximation, so you get in principle, when you consider this tunneling, right, you should consider all of the possible configuration that allows you for the transition. And here we just use the one that extremizes the action. So if we had a non-spherical bubble, which is supposed to extremize the action, I would say that maybe you would have get a smaller nucleation rate. I mean, if you add both of this type of solutions, that probably it would be bigger, right? But yeah, just having this one non-spherical alone, I think it would be overestimate a bit the nucleation rate. But to be honest, I'm not 100% certain about this.
Thanks.
Any other questions from the audience? Either put your hand up or unmute yourself. Maybe while we wait to have a question, Maciek. So you had a plot of the kind of action contributed from different orders or something like that as a function of radius, and then beyond some radius, you were in the tail.
Wait. I think this one.
Yeah, so here, so this RT is defined as like when the gauge field gets too light to be able to integrate it out, something like that.
Yeah, exactly. So so we define, like I defined it here as the moment where just this M3 is equal to the gauge mode. So this is exactly, as you say, the moment where there are two lights to integrate them out, because the actual derivative expansion will happen a bit later. So this is a bit more conservative estimate. Yeah.
So from this picture, it looks like a lot of the contribution of your kinetic term to the action is outside this radius.
Yeah.
Yeah. Okay. So I guess this is maybe a sign of the coming breakdown of the derivative expansion.
Yeah, because in the end, when you, I mean, okay, first of all, this position of this RT in principle is the RG dependence statement, right? When you consider the 3D EFT. But indeed, I would say that the fact that this is still large here kind of suggests that something goes wrong. And if you look at this here, at this orange line here, I would say what's exactly happening is that you overestimate this contribution, right? Because then your nucleation rate becomes larger. So if we were able to plot this Z factor exactly somehow, I think that it would be going to 0 faster than here, maybe.
I suppose that makes sense with what happens at higher orders, where the thing never goes to 0 at all and you get divergences.
Yeah, exactly. And I think that's like, because for the potential zero moment term, so this effective potential contribution basically, right? Like for LO and NLO, it behaves really nicely. But I guess it would also get spoiled even for the zero momentum term when you go to higher orders, because like I plotted once this three-loop potential thing from the final verdict paper, and it was also diverging there. So I guess that's might also be the same, the sign of the same disease, right?
Just comes a bit later on for the potential term.
Yeah, I mean, one can ask. I mean, so you evaluate it at the and on the whole, so bounce solution at the tail where you know it can't work, it shouldn't work. So it's kind of also a miracle or not that those two terms are finite at some loop order, but it's not maybe not so surprising that the other just diverge, because they shouldn't work then in principle in the first place.
Okay, thanks. So any more questions from the audience? No, then I guess we leave it there and thank Maciek again. Thank you very much.
Thank you.
Very pleased to have you. And see everyone in a month for Thomas Steingasser's talk.